We're being invaded by extraterrestrials. They might look like ping pong balls to you, but think of them as little particles, smaller than atoms, that have come showering down from the heavens, because that's what's happening right now. Through each and every one of us at this moment, particles, millions of them, are pouring just like the ping pong balls from the ceiling. Out there in space somewhere, maybe a star has exploded years ago and spewed these particles around into the electric and magnetic fields in the galaxy, which whips them into violent motion. And then a few passing the Earth, the magnetic arms of Earth grip them, pull them into the upper atmosphere where they smash into the atoms above our heads, breaking them into pieces, which shower down to the Earth, coming here in the theatre right now. We call them cosmic rays. They've been around ever since the Earth began. They're coming through us every second. People think that maybe this could cause mutations. Maybe this is how evolution is triggered. For our next stage of evolution in the world of the computers, there's a problem. You recognize the computer chip. Well, the problem of miniaturizing it. All the time, these little particles are shooting through could short-circuit these things, a problem still to be solved. Well, today we'll see these particles, and they already make themselves apparent to us in the beautiful northern lights. As the particles come in towards the North Pole, they hit atoms in the upper atmosphere and shake light out of them. And you see these beautiful images as a result. They're called the aurora borealis in the north and the australis in the south. Now, I can't take you all the way out there, but the beautiful images portray them clearly to you. They're actually happening here and now. They're coming through this theatre right at this moment. And what I can do with a special machine is to show them to you. Now, my colleagues at the Rutherford Appleton Laboratory and at Queen Mary Westfield College here in London have loaned us this thing here. It's called a spark chamber. Now, the reason for the name is fairly obvious. You can see the sparks, and it's a chamber. But what's going on inside this little box? Well, it's filled with gas, and there's metal plates and wires that are crossing it. And they're held at a high potential, high voltage. Now, if an electrically charged particle comes shooting through, it short-circuits the thing, and a spark jumps. So what you're seeing with these sparks is the passage of little particles, the end products of the cosmic rays that have hit originally far above our head. There's 6 miles of atmosphere above us that's shielding us, but even so, eventually they get down here to ground. And it's happening everywhere in the theatre at the moment. I mean, just imagine yourselves as you're sitting in your seats. The size of this chamber here is about the size of your shoulders and upper body. So every time a spark passes through here, there's probably one going through you right now. You just there. And you. But don't worry, all of us, all the time. You're just unaware of them because you don't have a means to see them. But over here we do. Nothing special about over here. I could put this anywhere in the theatre and show you that it's happening right now. Is there somebody here who's got confidence with me to see them passing right through us? Can I have a volunteer for this? Would you like to? What's your name?
Elizabeth.
Elizabeth, you stand on this step there so we can get up easily. Now, it's not going to hurt us at all. I'll put my arm in this end and you put your arm in that end. Hold the hand out so the cameras can see us. Now, what happens, every time a spark comes through, you can see it at the top, see it at the bottom, it's passed through our hands or arms. So this is showing the rays passing through us right now, just as they are through you. Do you feel anything?
No.
Nor me, nor anybody, but it's happening. Thank you. Now, this is a very small spark chamber, just to show as a demonstration device. In Geneva at CERN, they've got a very big one, about 2 meters large, and we went over there and got them to run it for us all night to take pictures of what happened. And at the end of the night, there was a handful of interesting ones, and we got them to make still photographs for us. Now, here's the first one. What's happened is that a cosmic ray has come in from outer space, and then it's hit something in the chamber. And where one came in, more than one has gone out. A particle has been created. The energy of these particles coming in from outer space is huge. Far greater energy than anything we have here on Earth at the present time in the room and around us, even greater than the energy in the sun. And that energy is being turned into matter, mass congealing out of energy, like at the start of the Big Bang. You're seeing it happening here, the creation of matter, when this particle hits in the chamber. And further pictures. Here, a lot has happened. Several particles have been created, maybe by a direct hit in the chamber, or maybe particles just created out of that pure energy. And the final picture, again, shows a lot of things coming out at the bottom, trails being created before your very eyes. So you're seeing particles, little particles being created before your eyes there in the chamber. You don't actually see the particles as such, you see the trails where they've been. So it's like seeing footprints in the sand and seeing what has gone on. You're seeing here the passage of cosmic particles. Now, the energy of these things is so huge, it's unlike anything we have around us here in the cool conditions of the universe today, 15,000 million years after the Big Bang. In the room, it's pretty cold. Go out to the sun, and you'll get into the conditions as they were 3 minutes after the Big Bang. And even there, the energies are not as extreme as these cosmic rays. There's something going on out there that is making these incredible energies, and it's as if nature is saying, hey, just a minute. I know that you've done experiments in the room here, and you've looked out at the sun, but there's a lot more. Those rays are coming in with energies similar to things that happened in the universe in the first second or so. And that's the trail we're going on. The discovery of those cosmic rays has shown us there's a great voyage to follow. Now, what we could do is follow that voyage by just watching the cosmic rays. But it took us all night to get that handful of pictures. What we want to do is to be able to recreate the conditions like those cosmic rays here in an experiment. And that will take us to the world of the particle accelerators, which will accelerate particles, speed them up until they have the same sort of energies that those original cosmic rays have. Then we'll be able to take that journey back and see what is going on. Well, that's where we're going to go today, but let's start the story at the beginning with the discovery of the cosmic rays. And there's so many things in these lectures. Let's just imagine jumping back the 100 years to the lecture in 1893, when they were very confident that they had found the solution to everything. They knew pretty well what the universe was about, they thought then. And then, a few years later, the discovery of radioactivity. And the modern science began at that moment. And it was that that led into the discovery of the cosmic rays. Now, what happened was this. The story begins with the Eiffel Tower, very surprisingly. What do I mean, the Eiffel Tower? How did that get in the act? Right, let me tell you. Radioactivity has been discovered. Everybody wants to go and find where it's coming from, what it is. And one way that they did this was to use a device called an electroscope. And we've got one here in the Royal Institution. Now, I'm going to reproduce an experiment here, and I need a volunteer to get the thing charged up to begin with. Would you like to come down? What's your name?
Stephen.
Oh, Stephen. Now, what we've got here is some fur. If you hold that in one hand, and then the rod in the other hand, and rub it really violently in the fur as hard as you can go. Really charge it up, okay? Now, the audience, you all watch the little gold leaf inside here, right? That should be pretty charged up now. Put the foil down there and just touch and rub across the top. See? They open up beautifully. You've charged up the gold leaf. Move it away gradually, put it down on the bench. Wonderful. Thanks very much. You've got the experiment started. So that's the first thing. Get the device charged up with the arms out. Now this is what happens if some radioactivity is about. I've got here a little source of radioactivity. Watch the arms when the radioactivity gets near. They just drop. So what you do, you prime up the electroscope, just like Stephen did, and then you go walking around looking for radioactivity. And if the arms drop, you know that there's some charged particles around, maybe radioactivity. That's what they were all doing. That was the thing to do in around 1900. But they were smarter than this. They knew that if they could shield this, then even the radioactivity wouldn't affect it. The discovery, though, was that however hard they shield their little device, radiation was still being detected. Now, radioactivity was far too feeble a thing to affect this when they got it shielded away. What was going on? There must be some new radiation around, much more powerful than the radioactivity. Well, where was that radiation coming from? Was it coming from the Earth or where? So this is how the Eiffel Tower got into the act. There was a Jesuit priest called Theodore Wolff who was carrying one of these things around Paris. Sort of held it near the Arc de Triomphe and nothing much going on. A few of these rays he detects making the thing discharge this way. So to see if it was coming from the ground or wherever, he walked up to the first flight of the Eiffel Tower. Now, he expected that the radiation would disappear because he thought it was from the ground, but it was still there. So he went up with courage to the second level, and the radiation was still there. In fact, if anything, it looked as if there was a little bit more, but he couldn't really be sure. So then he went to the height of his ambitions, to the very top. And it really did begin to look as if there was more radiation at the top than at the bottom. Now, at this point, he should have had the courage of his convictions and carried on upwards. But his head for height failed him. And the result was that the next year, 1911, an Austrian by the name of Victor Hess took the next great step by getting into a balloon and going up 5,000 meters with one of these things, and discovered an enormous amount of radiation. There was absolutely no doubt there was something new going on, and it was coming from the heavens. And it's Hess who is credited with the discovery of the cosmic rays, and it was Hess that got the Nobel Prize. So, many morals here, one of which is, if you have a good idea and you've got the courage of your convictions, follow it through. Don't let somebody else get the credit for picking it up and going the full hog. So Hess got the credits, and it was Mr. Wolff who started it off. So at 5,000 meters, where Hess had gone, you see more radiation, the cosmic rays. To really go up there and see the cosmic rays in their full power, you want to fire a balloon all the way up to the top of the atmosphere. And that's what people started to do after the Second World War. A team at Bristol University pioneered this, and we're going to repeat one of their experiments and show you how we go out and look at the vanguard of the cosmic invaders. So, bring me in our modern air balloon, Bryson, and we're going to reproduce the experiment. Thank you very much. Now, the first thing that I'll need is a volunteer to help me set the experiment up. Would you like to come down and do that? Right. If you hold the balloon in place here and don't let go, and turn around and face the cameras so we can all see what happens clearly. Now, I have got here a piece of film that we're going to put in the basket, and then in a minute, when it's all carefully loaded, we'll let that film go right the way up to the top of the atmosphere. Is everything in place? Are you happy? Okay, let go. And very slowly, the balloon will rise up, eventually high enough to take the pictures. Thanks very much. So there it is, up at the top of the atmosphere, waiting for cosmic rays to hit it, and then eventually we'll bring it back down to ground. But first, let's see a real experiment from 40 years ago from the Bristol University team. So here's their balloon ready to go up. And we run the film and we see it's about 50 yards of balloon here, gradually filling up with hydrogen gas, the ballast going away and it starts to rise. You can see the scientists moving around here, and there's experiments that they've attached to the end of this balloon, which are going to go all the way up to the top of the atmosphere to record the cosmic rays. Now, here's the last piece of weighting going up, and we will see the scientists move into view in the background, carrying their experiments, because they've worked for months on this, building these delicate experiments which are being attached to the balloon, and they don't want to damage them. So they're going to run with it and hold on to the last minute and remember to let go. Good Lord. And there it goes, up to the top of the atmosphere with the precious experiments hanging below it, just like our own experiment here in the theatre. Now that balloon is filled with hydrogen, and it'll be up there for quite a while, and gradually the hydrogen will leak out, and then it will come back to Earth. They can't guarantee where it lands. In fact, one of these things landed on the railway line between London and Bristol, and they had real trouble getting it back. But anyway, that's life. So we've got to bring our own experiment back to Earth. Now, can I have somebody help me to bring it back? Would you like to do that? Right. Pull her down all the way. Let's see what's happened. And when we get to the bottom, don't let go. Right. Okay. Is the film ready and exposed? Right, thank you. I'll hold on. Thank you very much. Would you like to take the balloon? So we've sent the photographs all the way up to the top of the atmosphere. Maybe some cosmic rays have hit them, and there's an image in here waiting to be developed, just like when you take a photograph in your own camera. You now take it to the developing laboratory. This is the point where we're on sort of Delia Smith's show when I say, here's one we did earlier. In fact, 40 years earlier. Let's see what came back from the experiment that the Bristol team had. Well, this is a typical picture that you find when you go up to the top of the atmosphere. But a cosmic ray has come in and it's hit the photographic emulsion. It's hit a bromine nucleus in the bromide and shattered it into pieces, all of which then come showering downwards, and they leave their trails here in the picture. Once the picture comes back to ground, you develop it, and in a sense, these little particles have taken their own photograph. This is the beginning of the shower of ping-pong balls that came down and hit me on the head. A cosmic football had come in from outer space and shattered the nucleus and showered them all down on me. You can almost feel the power in here. In fact, there's so much energy in the original cosmic ray particle that it's equivalent to being able to raise you almost a centimetre off the ground. All that in one particle. Now, what it is in nature that generates such amazing energies, to this day, we still do not totally know. But this shows you what you get when you go out and look outside and look out into nature and see what's going on out there. Now, we can show the cosmic ray story here. This is really where we've come. Here's the Eiffel Tower. Here's Hess's balloon. Here's the balloon we sent up with Bristol to the top of the atmosphere and brought the news back. So here's a cosmic particle coming in from outer space that has smashed into the bromine in the film in the high-flying balloon and broken it into bits, which have come shooting down, and they may have made secondary collisions high up there. Eventually, particles come shooting down right down here to the ground. Here's the Royal Institution. So the spark chamber, at the very beginning of today's talk, was picking up these particles, which were the long descendants of the original collisions high up there. Now, when the scientists started looking at what things were arriving down here and in these pictures, they found the sort of things they expected, like electrons and protons and neutrons, the stuff that we know about make up us. But they started finding other things as well. Things with weird properties, which they gave the name strange particles because they behave strangely. They also found something called a muon. You say, muon? What's that? I mean, we've got in our checklist, we've got electrons, we've got protons, we've got neutrons. What's muons? Good question. When the muon was discovered, Rabi, one of the leading scientists of the day, said, "Who ordered that?" And 50 years later, we still don't know. We're beginning to know, but we still don't totally know. Now, muons, I'll tell you what we do know about them. It doesn't take long to tell you. They're almost exactly the same as electrons. But for one thing, they're 200 times heavier. They've got 200 times more mass. And apart from that, identical. But why nature needs them, who knows? So this is an example of what happens. The moment you expand your ability to look at things beyond the room and out there, you find things that you previously weren't expecting. So, where have we got to? Well, we've got this vision. Here is the cold universe that we now are used to with atoms. The hot conditions of the sun and the cosmic rays have pointed us towards even hotter conditions. Great sources of energy, still today present in the universe. 15,000 million years after the Big Bang, there are still violent things going on out there, creating the huge energies similar to the Big Bang. Energy turning into matter in those cosmic collisions, just like the energy of the Big Bang turned into the matter that we're made of today. So what we want to do is to somehow recreate those things here on Earth. We're moving now to making the cosmic rays to order and studying what happens. And this is gradually going to take us towards the world of the particle accelerator. Why accelerator? Because we want to speed things up. We want to get energy into them and then smash them violently together to produce the conditions similar to the hot Big Bang. Because heat is things rushing around and smashing into each other. How are we going to do that? Well, one of the key ingredients brings us to magnets. Because magnets are lovely things. I've got some little demonstrations of what magnets can do. Here is a beautiful little executive toy that a colleague of mine, Colin Carlisle at Rutherford Lab, made. It shows you that magnets sort of influence the world around them. The magnet in the middle is sort of rushing around and the others don't seem to care very much, but when it stops, they all do a little jiggle. Let's just try this again. It's remarkably relaxing, you know, for tired scientists. There you go. I think this is so much fun. I'll just do it one more time. And if Colin's watching, I advise you to copyright this fast. I think this is going to be next year's sensation. There we are. A little magnetic dance. But magnetism extends over huge distances. What we have here is a binnacle, a compass from a ship. And this shows that you can travel all the way around the globe with this compass faithfully showing you where north is. Because the Earth is a huge magnet. And this is feeling the magnetism of the Earth. And I can make my own North Pole here. And as I move it around, it follows me faithfully. So you see the idea of magnetism extending over huge distances. And it's the Earth's magnetism that's trapping those cosmic particles and bringing them to us and whipping them violently into motion and smashing them into the atmosphere the way that we've seen. In fact, magnetism has got great power, and we can demonstrate some of the strength of magnetism. What Bryson has got here is a magnetic gun that we can even fire up to the top of the theatre. But for today, we're going to be rather safety conscious and just settle for demonstrating what magnetism can do. Go ahead, Bryson. I'll show off again once more, okay? You ready? Thank you. So, we've seen what magnets can do. They can affect things, they can move things around, they can give quite a lot of power when they move things around. That's one of the ingredients that we need in the particle accelerator. So here is the basic idea of a particle accelerator. We start off with electrically charged particles from atoms, like electrons or protons, say. And then we speed them up by giving them an electric kick, like a battery. And if you have lots and lots of batteries in a line, you can keep kicking them faster and faster and faster. And they'll go almost as fast as you like, as much energy as you like. You just need to make the line long enough. Now, it's not very practical to build a long accelerator that's 1,000 miles long. So what you do, you now bring in magnets to make it go around the corner. And that's what we have got here. The red things accelerate, and the blue things are the magnets that bend. Accelerate, bend, round and round the circle, as many times as you like. So with this, you can speed things round and round in circles over hundreds of thousands of miles. And then when they're going fast enough, you can then throw a switch and peel them off and make a collision, smash into a target, and see what happens. Because it's in that smash that you're reproducing the violent conditions of the early universe, and you're beginning to get a window on the start of time. So that's the basic idea. Electric fields to speed them up and magnets to bend them around. So we've got our own little accelerator here in the theatre. What I'll do is turn up the electric and the magnetic fields so that we can see a circle of electrons. There's a beautiful, eerie blue glow. That's the electrons going around in the circle, controlled by the electric and the magnetic fields, and it's shaking light out of atoms and the gas that's inside that sphere. Now, if I start increasing the strength of the magnets, they tighten the circle, just as a car going around a circle wants to spiral off the road if you go too fast. Let's see what happens. You see, if I put more and more acceleration into it, the things spiral larger. Turn up the magnets, and I bring it back and control it. So by varying the electric and the magnetic forces, I can make myself go on tighter and tighter spirals, keep the particles on track. And the power of your real accelerator is limited only by the power of the magnets to stop the particles spiraling off. Now, what we have done here is to build our own accelerator, and I've got it here at the front. Can I have a volunteer to help me drive the accelerator? Would you like to come down? Hello, what's your name?
Olivia.
Olivia. Right, now we're going to do this. This is a particle accelerator, and you're going to govern the speed that the particle moves, and then I will be the engineer making the switch to send it into the target where the collision is going to happen. Now, the way to do this is the dial that will speed the thing up. Do it very, very gently, okay? And then we'll gradually get it going faster and faster until the right moment, okay? But gently is the thing. Righty-ho, you ready? You do it. Round it's going. One more time, I think that's just right. Well done. Well, that is how it really is. I'm a theoretical physicist. I write equations on pieces of paper. I find experiment very difficult, but some of my colleagues are much smarter. They make it work almost every time. But this is a realistic representation of what happens. That it smashes into the target when it's going fast enough, and you saw these trailers come out. We've got some pictures of them. Here we are. That's what happens. The trails that emerge. It's just like that in the real experiment. That trails come out, and we have to decipher those trails to work out what the message is. And that's really the key part. It's the secret message in the trails. We're like archaeologists again. Here we've got some ancient hieroglyphs from ancient Babylon and Egypt, and they've got a secret message on them. I mean, there's clearly something important about these people on the back, and the message on the front must be telling us important news. The message is like the trails, if only we can decipher it. Now, if the Egyptologist can decipher these messages, then we learn about what happened in some marketplace 5,000 years ago. An important transaction took place and the message is here. If they can't decipher it, no use at all to anybody. It's a similar thing with us. If we can decipher the trails when the particles collided, then we can learn what happened 15,000 million years ago. And that is the path that we're trying to get to now. We want to find out what do those trails actually mean. Now, to do this, we need to have a nice camera. And the camera that was developed around 1950 was called a bubble chamber, and Bryson's ingenuity has made one for us. And Bryson, can you give us some bubbles? There we are, lovely bubbles. The idea of the bubble chamber was invented by Donald Glaser. That he has a big chamber filled with liquid that's about to boil. Now, I don't mean hot here. I'm talking about liquid like liquid nitrogen or liquid hydrogen. Very, very cold. The idea was that if it was very critically ready to boil, if a slight lowering of the pressure by lifting a piston and then putting it back again, if an electrically charged particle passed through in the moment that the pressure was off, then boiling would begin where the particle had been. And a little trail of bubbles would form, like the bubbles in here. Initially, they'd be so small you wouldn't be able to see them. But as they rise up through the water, they get bigger and bigger, and you can take a photograph. And from those trails, you're learning what happens when the particles collided. And this was a wonderful invention. It enabled us to look right inside the subatomic collisions, take photographs of them, the trails of where they had been. Now, Donald Glaser got the idea for this. He was thinking when he was a student about the bubbles in glasses of beer. You don't believe me? Go to your local library and ask if they've got a copy of the speeches that people give when they receive the Nobel Prize. And look for Donald Glaser and read what he tells you, and you will find that he was indeed thinking about the bubbles in glasses of beer. So it shows that you can always make good use of your time. There's always opportunity there. When you're enjoying yourself, the best ideas come. Now, this is a bubble chamber that I had hoped to bring to you here today, but as you see, it wouldn't get through the door. So we had to make do with the smaller version. But the pictures that you get are really like abstract art. And here is a typical bubble chamber picture. It's a picture of reality, of little particles doing their thing. It's as real as the pictures that you have in your family snapshots. But to decipher it, that's the key. Well, I'll show you how to decipher it in a moment, but let's see how you go about deciphering things in a very familiar way. If you see trails like this, you know what's happened, right? There's a small bear that's coming from this side, and there's a hiker that's coming from here, and there's a larger bear that's gone out in that direction. Now, this bit here, in the trade, we call the point of interaction. And that's what we're trying to find out about. And that's where we come to the critical question of decoding the trails. It's just like decoding these hieroglyphs. So how would you go about decoding something like this that you'd never seen before? And I'm sure many of you enjoy the game of writing coded messages and seeing if you can work out what they say. How do you do it? How do you crack the code? Well, what I remember as a kid was the first thing you need is to have lots and lots of examples, because the more examples you've got, the more chance you've got of finding the sort of common thread, which letters appear the most, how they join together, and gradually you suss out what's going on. Another important part of cracking the code is that you find a little bit that you can easily decipher, like the word the. You quickly recognise the word the and the word a. So that tells you where those letters appear in other places. So you do little controlled things, looking for the word the and setting it up. And that's what we do in deciphering these codes. What we can do is use some particles that we know and see what they look like in the pictures, and then decipher the big picture. Let me show you how. So here is a particle that we've shot through, and it's knocked an electron out of an atom. And by having a magnetic field around the bubble chamber, it bends the path of the electron, because the electron is negatively charged. Things don't change direction of their own accord. Things like to go in a straight line, unless you influence them. If you make a magnetic field, negatively charged particles will go one way and positives the other. Neutral particles don't leave any trail at all in these pictures. Now let's look at the next picture. If you really turn on the magnetic field, your electron will spiral round and round and round and round and round. As it slows down, the spiral gets tighter and tighter and tighter. It looks like the picture of a snail from the top or something like that. Now let's look at the next one. Now this has got a lot of information. It's a beautiful picture. At this point here, an electron's been knocked out of the atom and shoots off very high speed, curving very slightly. I know it's high speed because when you go fast, you only curve a little bit. If you go slow, it'll curve all the way around when you give the sideways kick. But look at this. Here is an electron that started off slow. It's really gone into a very tight spiral. But on the other side, there's the same thing going the other way. Negatively charged particles go one way, positives go the other. This, the red trail at the bottom, is a positively charged electron. The exact mirror image of the regular negative electron. It's an example of antimatter, captured here on film. This is antimatter. It's as real as the electrons are real. Now over here, an electron and its antimatter partner, which is called a positron, by the way, is produced. But between here and here, nothing appears to have happened. These appear to have appeared out of nowhere. Well, that doesn't make sense at all. What's happened is that something without any charge at all has gone from here to here and left no trail, but we recognize it was there the moment it did this. So we've got the steps in deciphering the pictures. Let's look at our original picture again and see if we can make sense of it. Okay? Well, this very faint circle here is just an electron kicked out of an atom, like the first part of our three pieces of the jigsaw puzzle. At this point here, we see a whole series of negatively charged particles curving off that way and positives curving off the other way. Then there's a gap where something without any charge at all must have gone, and it reveals its presence when it turns into two particles that do reveal themselves. So that shows you how you begin to decipher the picture. But in this picture, there's something very interesting. This gap here, a particle without any charge must have lived, and for a very, very short time. Let me show you what I mean. I've got this little clock along the bottom. This is the spot where this neutral object was created, and that's where it died. Now, what's this clock doing? Let's just think what happens in this thing here. We've got this bubble chamber and the camera taking photographs, and there's particles shooting in from one side, almost at the speed of light. They're across that bubble chamber in a flash. But the camera takes the picture, it's probably for a thousandth of a second, which is a short time to you and me, but it's a long time to a particle that's moving near the speed of light. It's as if the particle enters at this side of the bubble chamber and the clock starts. And by the time it's got to here, the clock is just past the starting point. And by the time it's got to here, it's a millionth of a second later. And by the time it's got to here, it's 4 millionths of a second later, and then it exits on the other side. But the camera shutter has been open all the time. And it takes what appears to be a still photograph, as you see here. But in fact, it's a time lapse. That time is running from one side to the other. So between here and here is maybe a millionth of a second or less. So this picture has captured the passage, the life and death of a particle that lives for less than a millionth of a second. It's astonishing to think that with this simple device, you can capture short timescales and make them for real. And that is as important a part of the universe as everything else. We've suddenly opened our perceptions in time here. With our unaided eyes, we can see a rainbow from red to purple, but we can expand right the way across the electromagnetic spectrum and see a great universe out there. Here, suddenly, we've expanded our senses in time to the very, very short. These new, unexpected, short-lived particles are as relevant to the universe, are as real to the whole picture as the things that live long enough to make you and me. And any rational explanation of the totality must include them. And that's the big challenge. Now, we're at about 1950, 1960. And as a result of pictures like this and lots of experiments with the accelerators, suddenly chaos. I mean, here we have been for 3,000 years from the ancient Greeks on the search for the ultimate pieces of matter. And around 1930, we thought we got it. Electrons, protons and neutrons. Not bad. Do everything. You and me, everything in this room, electrons, protons and neutrons. Then we found the cosmic rays, went and looked at them, started finding strange things and muons and other stuff. We build an accelerator, take pictures, we discover particles that live for less than a millionth of a second. Chaos. We've got all of these particles. We've run out of letters of the English alphabet, run out of letters of the Greek alphabet, more and more particles coming along. We have to find names to describe them. What on earth is going on? Well, people got to work on this, and they started noticing that, in fact, when you looked at them carefully, like butterfly collectors, they weren't all that different. Some of them actually looked quite similar. And we discovered that there were families in there. And the key to the families was this. Let's take a typical sort of particle discovered. Now, this has got some electric charge, maybe. 1 unit, 2 units, some number of electric charges on it. And it also, we discovered, has another property sometimes, has something called strangeness. Now, strangeness doesn't exist around here. None of us are strange. Nothing in this room is strange. Only things in cosmic rays and accelerators are strange. But on this plot, they decided to plot electric charge this way and the amount of strangeness in that direction. And this particular guy, who has no strangeness at all, happens to go just there. Now, in the cosmic rays, they had found some particles with strangeness, which, say, this one would fit just there. Nothing very exciting happening yet, until they discovered another one that went just there, and then something that looked quite related to that one sitting there. It's interesting, you know, I could have put these things all over this board anywhere, but they started seeming to clump in this little region, and they got quite excited when they discovered another one that sat just there, and began to think maybe there's something missing that if I looked hard I'd find it. Well, almost, but not quite. The next thing that turns up is down there. Got the pattern yet? Well, the ideas were really proving to be on the right track when this one turned up, and they were really on the right track when that one turned up. Now, there was 2 guys had the idea that they thought they knew what was going on. One was called Yuval Ne'eman, an Israeli, and the other one was Murray Gell-Mann from the States. And they already perceived that in these patterns, these families that were appearing, little triangles seemed to be buried. And one day they were at a conference in Geneva in the early 60s, and a person was standing up giving the results on the latest discoveries in the bubble chambers, and announced that they had just discovered a new particle, and it had certain properties and so on and so forth. And Gell-Mann and Ne'eman were sitting in the hall, and the moment that the lecturer announced the properties, Gell-Mann and Ne'eman both realised that it fitted perfectly into the scheme that only they knew about. Neither of them knew the other guy knew about it. And at that moment, they both thought, Eureka, there's one more that will complete the scheme. Both put their hands up. And the chairman saw Gell-Mann, who was sitting near the front, and called him out at the end. And Gell-Mann said, as a result of the announcement that's just been made, I predict that there is a particle waiting to be found that has strangeness 1, 2, 3, and will sit there in my pattern, because I believe there's a big triangle behind all this. He says, I know exactly its properties. It's got negative charge because it sits there, and because it is the last particle that will prove my scheme, I will call it the omega minus. Omega for the last, and minus because it has minus electrical charge. And within a few months, the scientists looked through their pictures and they discovered a particle with exactly the right properties, and it proved that this idea was right. And all of the particles that kept turning up fitted into these families of either a big triangle or shapes like that. But even in this sort of family, you can see there's the triangles buried in it. So that was the idea of the triangles buried in these families. Buried in. That's a clue. Could there really be some triangles buried inside these particles? Could it be that we're beginning to realise that we're on the trail deeper into the cosmic onion? That there are, in fact, things buried inside there. And if we could peel the onion back, we could see them. Now, the proton is one of these particles, and the idea, if there really is something inside, let's go and look. Well, that was difficult. The best they could do at that time was to look at the proton and make it appear rather fuzzy. They could see it wasn't exactly a little point, but they could see that it had some size and it was fuzzy. Bryson, show us your fuzzy proton. So this is what the proton looked like around 1960 with the most powerful accelerator, the most powerful microscope that they could look at it with. It was a diffuse, broad object. Now, the idea that there might be something inside it required you to look inside with a much sharper microscope. And that was done in this machine here at Stanford in California. At the back of this, they use electrons are produced and accelerated through 20,000 million volts along the 2 miles of the accelerator, and at that stage they're powerful enough that they can look inside the proton and see what it's like. And this is what they found. That as the picture got sharper and sharper, they began to realize that the proton wasn't completely diffuse, but there appeared to be something in there. And around 1970-72, the results of the machine at Stanford and also at CERN in Geneva showed that there really were 3 things inside, things that have become known as quarks. And so we've seen them. There they are, a deep layer in the cosmic onion. All of those patterns have emerged as a result of these 3 quarks inside the proton. Thank you, Bryson. Now, I have a love-hate relationship with quarks because I've spent 20 years of my life working on them. And they are indeed another layer of the cosmic onion. It's quite possible that they are the deepest layer in the onion. The original particles of matter, or at least the matter that we're all made of, created very, very early after the Big Bang. But what kind of creature are they? How do they behave? How do they link together and build up matter as we know it? Those are the questions that we and my colleagues have been trying to investigate for the last 20 years. When I was a student, I was asked to think about these things before anybody had even seen the fuzzy proton turn into a real sharp picture. And I thought it was pretty crazy. Luckily, it turned out to be right. And as a result of experiments over those 20 years, this is what we know. Bryson, bring on the quarks. Well, the good news is there's only 6 of them, and they do everything. They've got fanciful names like up and down and strange and charm and bottom, and the one we know is there and we're on the hunt for at the moment, top. Now, when Gell-Mann first came up with his idea, only 3 of them were needed. That was all that we knew of at that time. In fact, to make the stuff inside you and me and everything around here, only 2 are needed, the up and the down. The strange particles that had shown up in the cosmic rays required the 3rd type of quark called the strange. And it was these 3 that were the seeds behind those patterns. This was the triangle, suddenly come alive, these 3. In fact, that's why the name quark became invented. That Gell-Mann loves literature, and he was reading James Joyce's Finnegan's Wake. And in there's a phrase, 3 quarks for Muster Mark. And so because he wanted 3, he came up with the name quark. Now, there's been a lot of discussion about how you actually pronounce the word. Is it quark or is it quark? Now, the literati among you will say, well, it's quark because it rhymes with Mark. But then the next stage along is to say, yes, but Mr. Mark was actually a publican who was serving beer, and it was really a pun on the word quart, as in a quart of ale. So it should really be quark to rhyme with quart. But those of you who know more know that Joyce was Irish, and that with the Irish accent it's 3 quarts of ale. So it's quark to rhyme with quart. So what's in a name? Well, that's what Gell-Mann knew. Today we know more. In 1974, it was discovered that particles existed with a property we call charm, and that's because they contain quarks with charm, charmed quarks. In 1977, we discovered the existence of the bottom quark. We now believe there must be a top quark to complete the pattern because we see them 2 by 2 by 2. And this is one of the great mysteries. You see, the up and the down quark are sufficient not just to make everything around here, but the best theories that we can write down seem to work perfectly well if that was the whole menu. For some reason, nature seems to have made a set of photocopies that are heavier, but identical in all other respects, the strange and the charm. And we also believe it's made a third set of photocopies, the bottom and the top. Why? I don't know. I do know from experiments at Geneva in the last couple of years that that at least is the end of this story, almost certainly, that the matter that we know is made up of these three lots of twos. Now, to make it even more bizarre, let me show you something else about them. If I turn them around, you will see that the up quark has got an electrical charge of 2/3 and the down quark of -1/3. These are in units where the proton has got 1 unit of positive charge. The strange, -1/3, and the charm, +2/3. The bottom, -1/3. You getting the picture now? We predict that the top, when it's found, will have a charge of 2/3. Now, this is very odd. I mean, when I was a student and I was asked to think about quarks before we even knew about them, they seemed pretty idiotic enough anyway, let alone the possibility that they were supposed to have charges of 1/3 and 2/3, when all the books I'd ever read said the smallest charge that you ever find on its own is 1. So here I was being asked to think about something that was a complete and utter nonsense. It turned out that's the way that the universe works. Nobody has ever produced one of these quarks on its own. Now, at this point, often in lectures, people think, just a minute, I mean, we've sat through all this, it's got pretty bizarre, and now he's asking us to believe that the final layer of the cosmic onion is something that doesn't exist. I didn't say it doesn't exist. I said it doesn't exist on its own. These things certainly exist inside the protons and neutrons. With that powerful microscope, we were able to look inside and see them there. The proton and neutron are like an ideal prison, with the quarks inside. They can't escape, but you can see them there if you've got sharp enough eyes. Let's look at the proton and neutron in terms of the quarks. And here they are. Your neutron is made of 2 down quarks and 1 up quark. 2 lots of -1/3 and 1 lot of +2/3, with your pocket calculators, should add to 0. The neutral neutron. The proton has got 2 ups and 1 down. 2 lots of 2/3 and 1 lot of -1/3 gives you +1, the 1 unit of positive charge of the proton. It looks as if God is a mathematician. But the $64,000 question is, what holds those quarks together to keep them bound so tightly inside the protons and the neutrons? There must be some new force around. Yes, there is. We call it colour. It's a new charge, like electric charge. Just like electric charge gives rise to the electromagnetic forces, so the colour charge gives rise to new chromomagnetic forces. And the rules are just the same. Unlike charges attract and like charges repel. And they build up for us the protons and the neutrons, and more. Let's just have a look. So deep down there in this bottom layer of the onion, we find the 3 quarks, and the little wiggly lines are to represent this sort of force, this colour force that's holding them together inside, to build up the neutrons and the protons that are the seeds of matter. Now, that force exists very strong inside the neutrons and protons, but it leaks out a little bit, and that's what this on the outside is simulating. It leaks out enough to hold neighbouring neutrons and protons together, to build up atomic nuclei. So the powerful forces that hold the nucleus together inside all of our bodies ultimately comes from the little colour forces between the quarks inside those neutrons and protons. So if the colour force were not there, we wouldn't be here either. It's essential to our existence in some very profound way. And this really brings me to the pinnacle of this tale. There's something really bizarre going on. An incredible coincidence, but I don't believe in coincidences. Let me tell you what it is. We've got 3 different colours available. It's 3 shades of this new charge. We call it red, blue and green just for a name, but there's 3 of them. And it obeys the very same rules as electrical charges do. Like colours repel, unlike colours attract. Now, there's only 3 of them available. So if a 4th one comes along, it's bound to get repelled. That's why they cluster tightly in 3s, like this. The electrical charges on the quarks are 1/3 and 2/3. It's the 3 colours and the 1/3 of the charge conspiring together to give the proton its total charge of +1, sitting there in the centre of the atom. On the outside of the atom are the electrons with negative charge, 1 unit of negative charge, exactly balancing the positive charge of each and every proton. One of the most accurately known numbers in physics, the equality of the electron and proton's charges. You're proving it right now. There's millions and millions and millions of atoms inside you, each one containing negative electrons and positive protons exactly balancing out. How on earth do these electrons, which have nothing to do with these quarks, know that their charge is exactly balanced by the charge inside the protons? The charge of the protons coming from the 3 colours conspiring with the 1/3 charges. You really feel that something deep down is going on. That perhaps there's only one type of matter, one basic form of particle, that sometimes appears as an electron, and if you paint it with the colour charge, manifests itself as a quark. And that really is the first hint that deep down there's a unity in matter that previously we hadn't seen. If we're going to get on the trail of that, we're going to have to go back to the era not when the atoms, nor the nucleus, nor even the protons and neutrons were being made, but right back to the point where the quarks, the seeds of creation of matter that we now see, were being formed in the Big Bang.